recording, supposedly. All right, now, okay, so we're going on to chapter 7. And like I said, chapter 7 is not going to take long to go through. All right. Beauty of chapter 7 is that it's descriptive and it's just what I'd call a lot of hand waving. Okay, there is some there's science behind it, obviously, but it's a lot of there's not any calculations per se, is what I'm getting at. Okay, so we have this periodic table in front of us, and we have been using our periodic table, and we've looked at it and um, and so forth. Now let me pull up. I'm going to need a different periodic table from this. So what I'm going to do is I'm going to go ahead and pull up another periodic table. And let's see if I can type this in here. Periodic, because I want one with the masses on it. All right, periodic table, and we try to find ourselves one. That's not the one I want. And here is, oh, this one's a nice one right here. All right, so I'm going to copy the image, and I'm going to go ahead and paste this. And let's make sure that I can paste it, Control V. And so sure enough, I have a periodic table. There we go. Everybody see the periodic table? Yes, thank you, Crystal. You're the only one that I can see. So, there you go. All right, so we have this periodic table in front of us, and there is a graph. Let's see if I can actually write on this, and I can. And there's a table of a periodic table on page 258. On page 258 is a periodic table, which I have seen this periodic table or some version of it on page 258, and it's fascinating. At least it is to me, from a sciencey sort of, geeky sort of nerdy sort of standpoint, which I am. Be true to what you are. And I see this periodic table. Now look at it. If you have it, it is it's truly amazing, because if you look at it, ancient elements that we knew, 9, just 9. And then you get into the Middle Ages of 1700, and we had 6 more elements, and that's it. And then it wasn't until the 1800s, the mid 1800s, that we started picking up some more elements. Mid 1800s. Now, 1800 seems like a long time ago, but in the grand scheme of things, it is a blink of the eye. 1800s, we're talking a little over 200 years ago. Most of the periodic table, they had no idea what was there, most of it. So to me, that is like pretty neat. We live in exciting times, believe it or not. You're going to be born in some time, believe it or not. This is probably one of the best times to be born. All the really cool stuff's happening. And now, we knew about all these elements, and one of the things that came along was that we figured out, scientists and alchemists and such, we figured out that certain elements seemed to behave in a similar sort of way, and they were actually grouped in families. Now, it took Mendeleev and a couple other guys to actually figure out that we had these things called groups. You had your carbon group, your nitrogen group, oxygen group. What makes a group a group? It's a column, but more importantly, they share chemical properties. And so if you arrange the periodic chart, the periodic table, in terms of groups, then with a little bit of manipulation, you end up with something that looks a lot like the modern periodic table. Now, we have the benefit of hindsight. There's no empty spots in this table, but at one point, if you look on that, what I just showed you, there were lots of empty spots. And so the periodic table originally was organized by increasing atomic mass. And you may say to yourself, well, look at hydrogen's 1, and we got helium's 4, and lithium's 7, and beryllium's 9. It's going in order. What's the big deal? It is going in order, right? If you go by mass. But if you go down, and this is a common mistake to assume that the periodic table is arranged in order of mass. If you look at These guys right here, they're in order, right? Go iron, cobalt, nickel, but look at the masses. It goes 58.8. It goes 55.8, then it goes 58.9, and then it goes down 58.6. If you were to put these in order by mass, you would actually switch cobalt and nickel with each other. If you went by mass, if you were to measure these things, and you would predict that cobalt would be with palladium and platinum, and it would behave like an oddball. It wouldn't behave right because cobalt doesn't behave like nickel and palladium and platinum. You see what I'm saying? If you put them in order by mass, you end up with some problems. And it took actually not Mendeleev, but some other fellow, I think it was Seaborg, I think, or one of these guys. He actually did some X-ray studies, and he was the one who determined that the element is based on the number of protons. You see this? Number of protons, or the atomic number. And so if you arrange these guys in increasing atomic number, then we get the modern periodic table. Okay. So prior to realizing that it was the atomic number, or the number of protons, that determined the element and what group you ended up in, there were some competing versions. Okay, so this is one of these things that you may not notice, but now that I've shown it to you, you will never be able to get it out of your eyes. It's kind of like you can't unsee this once you've seen it. That in fact the periodic table is not in order by mass. It sure is not. It's in order by atomic number. Now, within the groups, and we just covered this in chapter 6, within a group, they have the same outermost electrons. They have the same valence electrons. Like, for instance, the nitrogen group would be what? It would be NS2, because, it goes 2s2, 3s2, 4s2, whatever, 2s2, 3p3, and like fluorine would be the whole, and I say all of them, we just went over this, but all of them would be NS2. Oh, leave off, sorry about that. I got so carried away with the row number. It's NP3. It would be N, not NS2, but NP, what is that? NP5, right? Okay. So it'd be NS2, NP3, NS2, NP5, for nitrogen, fluorine, respectively. And what does that mean? These are the valence electrons, and they share the same valence electrons. Now, you accept as given that the periodic table is arranged like this, and there is no reason why the universe needed to be created this way. It's how it worked out. It worked out, and it's pretty neat that it worked out this way. Very few things in nature are like this, where they follow these very clear patterns. Most things are not like this, is what I'm getting at. Okay, and so this is actually pretty cool when you think about it, that nitrogen behaves a lot like phosphorus, phosphorus behaves a lot like arsenic, oxygen behaves a lot like sulfur, and sulfur behaves a lot like selenium. And then if you know the chemistry for one, you can make some sense out of the chemistry of the others. And matter of fact, germanium was one of the elements that was discovered by looking at the elements that were around it. Germanium was one of these elements that there was a hole in the periodic table. They knew there was an element that was supposed to be there, but they didn't know what it was. And so there were predictions made. Well, we predict that the atomic mass is probably going to be around 73. It's going to have characteristics similar to silicon, and so forth. And then they went forth and looked for it, and there they did. They found germanium. Guess where germanium was found? In Germany. That's why it's called germanium. Okay, so it was found in Germania, you know, Germania. Yeah, well, that's actually an old name for Germany, by the way, is Germania. And so it was found in Germany. Yeah, and I can't say it. I know. It's such a you know, you get it set on your brain, you know, that you're going to say it a certain way. So the periodic table is arranged the way it is because of that. Now let's do a quick tour of the periodic table. These guys right here, these are called the alkali metals. These are the alkali metals. These are the alkali earth metals. These are the transition elements, right? These are the boron elements. By the way, these are called poor metals. This is not listed in a lot of textbooks. These are actually poor metals through here. These are your metalloids. And then you got your halogens over here, and you got your noble gases over here. Okay, so we should know the general layout of where the periodic table is. Most importantly, where are the metals? Metals, non-metals. All right. Why is it important non-metals versus non-metals? Because that's how you do ionic compounds and naming and so forth. Okay. All right. Now, there are some periodic trends, and before I say that, take some time to read. Here's an assignment for y'all to do. Read about the group 1 elements. Read about group 1. There's some stuff about oxides, superoxides, and so forth, superoxides. And that's over on page whatever. It's with the alkali metals. Okay, group 1 has some interest in oxide chemistry. They just threw it in there. It's not because it's super important, but it's just there. Okay, so read that when you get a chance. All right, so let's go over periodic trends, which is kind of like the whole point of chapter 7 is periodic trends. We're going to get into the hand waving now. Okay, so size or radius. Let me find a point where I can do size of atoms, or radius. If you want to get really technical, it's radius. Okay, as we go left to right, we get smaller. As we go top to bottom, we get larger. Okay, this is your first trend. So size or radius, as we go left to right, we get smaller, and we go top to bottom, we get larger. And you may say to yourself, well, if you think about it for a second, the top to bottom part should make sense. You're getting bigger and bigger atoms as you get further and further down a period. How about left to right? Now left to right should not make sense because you're going from say here to here. I would expect them to get bigger as you go left to right because you got what? You got more stuff. You got more electrons, you have more protons, you have more neutrons. It should be bigger as you go left to right, not smaller. All right? And it's the other way. It goes the other way, and I'm going to tell you why. And it looks like this. Let me show you. As you go left to right, what happens? You go from You have a proton with an electron that's whizzing around, okay? And as you go left to right, you pick up another proton. You also pick up another electron. All right, everybody with me so far? All right. Now what happens? See, the proton is attracting the electron. That's what's holding on. The plus and the minus are attracting each other, and that's what's holding it on to the atom. Now you get over here, what does this electron see now? It sees two protons, which means it's pulled twice as hard in. And so it'll actually move in a little. And so its new position is in a little closer. Now, it also, of course, the other electron that's over here is also pulled in. And so compared to where it was, it's now a little closer. And if we go across the periodic table, as we see more and more protons, we get closer and closer and closer in. And so this force, these additional protons, is pulling the electrons in. Now, if we complete a shell, we leave off where we're at, and then we start all over again with the next electron on the outside. So as we drop down to the next row, we complete the shell, and then we start adding on top of the shell. So we go like this as we go across, but then the next one has a shell on the outside. So we're doing it all over again. See what I'm saying? So sure enough, as we go top to bottom, we get bigger. And as we go left to right, we get smaller. Smaller from left to right and bigger as we go top to bottom. Okay, so that's your first trend. So our first trend for us is radius. And that is left to right, bigger, and top to bottom. It's early, it's Monday. Left to right, smaller, top to bottom, bigger. Okay, it eventually made it onto the paper correctly. Okay, so left to right, we get smaller, top to bottom, we get bigger. Okay, now, what are we seeing? What we are seeing is the charge of the protons is what we're seeing. Okay, that's what's drawing in the electrons. More on that in a little bit. Now, for ions, left to right, top to bottom, it's the same. You get smaller as you go left to right, and we get bigger as we go top to bottom. So as we go across the periodic chart, as we go lithium plus, calcium plus, aluminum plus, whatever, they're going to be still going to be smaller as we go left to right. All right, as long as that charge is the same. And you may be saying to yourself, well, wait a minute now, isn't calcium 2 plus? And I wrote down plus. Well, I'm saying if you keep all things the same, then they will be smaller as you go across. Okay, so what does that mean? It means as we go, also it means as we go from a sodium to a sodium plus, as we go from a neutral to a cation, it'll be smaller because what have we changed here? We haven't changed the number of protons. All we've changed is number of electrons, and so there's less stuff. So cations are smaller. As we go from chlorine to chlorine minus, we get larger. So anions are bigger or larger. Why? Because you've got more electrons, you've got more stuff. You're not changing the number of protons. So in this case, we have, we're not changing protons. When we ionize something, when we change it from, say, a neutral ion to a positive ion, we're losing electrons. Not changing what it is. And so it really comes down to more stuff, less stuff. More stuff, less stuff. You got more electrons, you got more stuff, it's bigger. Same atom though. Sodium to sodium plus, you lost an electron, it's still a sodium, therefore it's smaller. Chlorine, chlorine minus, you gain an electron. It's still a chlorine, therefore you added more electrons, it's bigger, okay? All right, but if you're all positive charged or all negative charged all the way across with the same charge, then it's going to still follow the same pattern because now we're changing the number of protons. In other words, we're sucking things in. All right. All right. Now, we have something called the isoelectronic series. And here's something that's kind of isoelectronic series. All right, so what do we have so far? We have, as you go left to right on the periodic table, what happens? Ions and neutral atoms, they get smaller as you go left to right, and they get bigger as you go top to bottom. Isoelectronic, you have to throw all that out the window. All right, isoelectronic, iso means same. So it means same number electrons, okay? Now, if you have the same number of electrons, here's the key. If you have the same number of electrons and you're different atoms, guess what? You have different numbers of protons. Okay? So an isoelectronic series, let me pull out my periodic table here. An isoelectronic series might look like this. We might have, here's one right here. So we might have, let's say, N, we would say N 3 minus, we could say O 2 minus, F minus, Ne, neon, and then we could say sodium plus and magnesium 2 plus. This would be an isoelectronic series. Why is it isoelectronic? Because it's the same number of electrons. If you look at neon, neon has 10 electrons. If you look on your periodic chart, sure enough, you see neon is element number 10. But if you add an electron to make it F minus, well, what does that mean? It means you start out with 9 and now you have 10. You look at oxygen. Oxygen starts out with 8 electrons. You add 2 in, you have 10 electrons. Nitrogen, same way. You start out with 7 because nitrogen is element number 7. You add in 3 electrons. That's what 3 minus means, is you have 3 extra electrons. You have 10 electrons. So you have 10 electrons on that atom all the way across. Neon being the only neutral one because it has 10 protons and 10 electrons. Okay, so it's neutral. Look at sodium. Sodium is element number 11. If you drop off 1 electron, you have 10 electrons. And what does it mean to be plus? To mean plus means you're missing an electron. So once again, we have 10 electrons. Same thing with magnesium. Magnesium 2 plus means you're missing 2 electrons, right? What's magnesium? Magnesium is element number 12, so we're back to 10 electrons. So all 6 of these elements, all 6 of these ions and the neutral neon, all 6 of these have 10 electrons. They are isoelectronic. And so out of this series, what's the largest? What's the smallest? Because that's about all you can say about these isoelectronic series is who's the largest, who's the smallest. Now, if you're looking on the periodic table, here's where common mistake. We look on the periodic table and you say, you know what, Mr. Pierce, I've got this. All the way on the right-hand side, this must be the smallest over here, right? And therefore, as we go further across it, this must be largest, right? Because where is it? It's the next row down, right? It's the next row down and it's bigger, and you would be wrong. And you would be wrong. Why are you wrong? Because see, these are not neutral elements. If you're adding electrons and adding protons, sure enough, you're going to go left to right. You're going to get smaller because they're going to get sucked in, right? And as you drop down to the next row, you're completing a new shell. But we're not completing anything here. These are all for nitrogen. That would be 2s 2p6 for all of these guys. This is 2s 2p6. This is 2s 2p6. It was 3s1, but we took off that 3s1. It's gone. This was 3s2. We took off the 2. It's gone. You see what I'm saying? Same thing over here. Where did we add it in? We went from 2s2 to 2p7, but we added in one more to make it 2p6. It's 2p5, sorry. 2p5, we made this 2p6. Same thing. So they're all the same electronic configuration as you go across. So what's different? The number of protons. And so this has, the nitrogen has what, 5 protons, 6 protons, 7 protons, 8 protons. This has 9 what is it? I'm losing count here. I need to have my periodic table in front of me. Nitrogen is, yeah, it's 5. Nitrogen, no, 7, sorry. My eyes are getting crossed. So it's 7, 8, and 9, 10, 11, and 12 protons. 7, 8, 9, 10, 11, 12, 9, 10. That's supposed to be a 10. Okay, 10, 11, 12. So what's happening here? If you have the same number of electrons, right, in the same shell, what's happening to those electrons as you add protons? They're getting sucked in. So what's going to be the smallest? The smallest is going to be the one with the most protons. Smallest is going to be your magnesium 2 plus. It has 12 protons. It has 10 electrons. What's going to be your largest is the one where the electrons are not held on the tightest. When this, so nitrogen would actually be your largest one because it has 10 electrons, but it's being held on with only 7 protons. Your magnesium is smallest because it has 10 electrons and it's being held on with 12 protons. So it's exactly the opposite of what you would, it's not quite the opposite, but it's different from what I just told you, which is left to right, you get smaller, top to bottom, you get bigger. When you hit here, you're still the same shell. The only difference is you're adding more protons. It doesn't matter where you're at on the periodic table. If you have the same number of electron, different number of protons, it's going to suck it in there more if you got more protons, regardless of whether you've started a new row or not. The row is a human construction. It's what we put together. Nature says, you got 10 electrons, you got 12 protons, you're going to be sucked in more than someone who has 10 electrons and 7 protons. So the largest in this case would be the N3 minus, and the smallest would be the magnesium 2 plus. Okay, so don't get these two confused. Isoelectric is not the same. Okay, when we say left to right small and top to bottom bigger, we're talking about neutral atoms. Neutral atoms, okay? Neutral atoms are atoms with all the same charges. In other words, there's no difference. As you add electrons, you're adding protons, okay? All right. In this case, you're not. So you can pick out any isoelectronic series, and I can make up one for you right quick. Like, how about let's have sulfur, chlorine, argon, potassium, and calcium, and it would go 2 minus, 1 minus, 0, plus 1, plus 2. Well, there's an isoelectronic series right there. This sulfur would have what, 18, 18, 18. Potassium plus 1 would be 19 minus 1, which is 18 and 18. They all have 18 electrons. This is an isoelectronic series. How do you tell if you're dealing with an isoelectronic series? They all have different charges. That's how you tell. Everybody has a different charge, and they're all, you know, you got a 1 with a 1, a 2, a 3, and a -3, and a -2, and a -1, and a 0. You've got an isoelectronic series. How do you tell which one's, well, so biggest, smallest. So who's the biggest? Who's the biggest out of the bunch? It would be the sulfur, wouldn't it? Who's the smallest? It would be the one with the most protons, and that would be the calcium. Okay, even though this is on the next row. You see what I'm saying? That's where people get tripped up on this. Even though it's on the next row, it's still smaller. Why is it smaller? Because you got more protons. More protons, you suck any electrons in. You have the same number of electrons, so that doesn't change. So the only thing you're changing is the positive charge that's on the inside, okay? All right. All right. So what do we have so far? We have for atoms, as we go left to right, top to bottom, we get smaller and we get bigger. For isoelectronic, we go from large to small with increasing protons, right? We go from large to small with increasing protons, and we have to say, ignore rho for isoelectronic. Okay, we have to do that for isoelectronic. Let me clean this up so it looks a little neater. Isoelectronic. Isoelectronic. All right, now related to all of this is something called ionization potential, or IP. And that's how tight electron is held. Okay, that's what ionization potential is. How tight the electron is held. And the technical definition is the energy to remove one electron completely. One electron completely. That's the technical energy, the technical definition. Okay, so you have an atom, you yank the electron off completely. All right, and it is related to this guy right here. What's holding the electron on? The protons, right? And so what's determining the size? As you go from left to right, it gets smaller, right? Why does it get smaller? Because it's being pulled in tighter. And if you're holding on tightly, then it's going to take more energy. So for ionization potential, as you go left to right, just like the diameter decreases, the radius decreases. Since it gets smaller, then it's going to take more energy, and so the IP goes up, or becomes. By the way, there's a sign convention to this. Becomes more negative. Okay, that's important. Becomes more negative. Okay. By the way, if something has negative energy, it means you have to put energy in it to get it to come off. Okay. Hold on. Change that to positive. It's always positive. That's my mistake. All right. Always positive. All right. Because you got to put energy in. All right. So ionizations are always what they call endothermic. They take energy to do. All right. And so as you go left to right, the IP goes up. And as you go top to bottom, the IP goes down. Why does it go down? Well, as you're going further down the periodic table, what's happening to the diameter? It's getting bigger and bigger. So you're further and further away from those positive charges. See what I'm saying? You got the positive nucleus. If you're further away, it doesn't take as much energy to pull it off because you're already that far away. Okay. So the IP generally goes up as you go left to right, and it generally goes down as you go top to bottom. And it follows the same sort of trend of atoms getting smaller, atoms getting bigger. And it's the same sort of thing. It's how much you're holding on. Okay. All right. So that's ionization potential. And the last one that I want to cover here, as far as periodic trends go, like that, is something called electron affinity. And then we'll do Z and then we're done. Electron affinity. And that is really, it's how much does an atom, how much does the atom want the electron? And if it's negative, then it means it wants the electron. And positive, it absolutely does not want the electron. Does not. Okay, E minus is shorthand for electron. Okay, and generally the way it works is like this. Over on the right-hand side of the periodic table, on the right, not left to right, but on the right is generally highest, E of A, electron affinity. And generally speaking, on the left-hand side, it's the lowest, E of A, generally, okay? And in the middle, all sorts. Okay, it's not a left to right trend. Okay, it's not a left to right trend. It's just on the left, you generally have the lowest electron affinity, and on the right, you generally have the highest electron affinity. And there's some discontinuities in there. Your alkali earth metals actually usually have a lower electron affinity than the alkali metals, even though the alkali metals are a little bit to the left. But the general trend still holds. On the left-hand side is mostly your lowest, and on the right-hand side is mostly your highest, okay? And we'll just leave it at that, okay? We'll just leave it at that. All right? Okay. Now, those are your trends, at least some basic beginning trends. All right, now, Z. Z is the nuclear charge, which equals the number of protons. All right, that's Z. Now, there's something called Z effective. Z effective. And basically, there are all sorts of ways of calculating Z effective. And the idea is that the further you're outside of an element, the less you see of the nucleus. And if you have shells that are in between you and the nucleus, they shield and they keep you from seeing the nucleus. This is the whole idea of, as you go down the periodic table, they get bigger. But part of the reason is that these electrons out here don't see the nucleus as well as, say, these guys do. Okay, it's like I said, a lot of this is hand waving. And so there are all sorts of ways of calculating Z effective, and the book goes into several ways. And I will tell you, there's really only one way that matters, and that is you take Z, which is a nuclear charge, and you subtract off Z core. And what is the core? Previous shell. That's all it is, previous shell. There are all sorts of ways of calculating Z effective, all sorts, where you count for S's and P's and D's. And oh, by the way, the further you're out, the less shielded that you're going, the less shielding you're going to experience, the closer you are to the element. So S is closest, so it experiences least amount of shielding. P is even, it experiences more shielding, and D is even more shielding because it's further and further away from the core. All right, now here's how it works. Real simple. Let's say what is Z effective of, let's pick one. How about chlorine? What's the effect of a chlorine? And if you look in the textbook, there's about a half a dozen different ways of calculating Z effective, depending on, you know, how much weight you pay on, how much weight you put on the S's, how much weight you put on the P's, how much weight you put on the D's, whatever. And what I'm telling you is Z effective, you take the number of electrons of the chlorine. What's chlorine? Chlorine is 17 electrons because it's element number 17. And you subtract off the previous shell, which is 10. And Z effective is 7. Where did I get that 10? That's neon. So Z effective of chlorine Z effective is 17 minus 10, which is 7. Now, are there much more sophisticated ways of doing this? You betcha. There's all sorts of sophisticated ways of doing this, where you'd get like 5.78 or 8.91 or whatever, okay? And unless you're a computational chemist, you don't care. And even if you are a computational chemist, you still don't care. It's one of those kinds of things. You calculate it once, you put it up there, like I said, hand waving. You show it one time and you go like, yeah, that's nice, and you move on, okay? But that is what Z effective is. This is the screening electrons. So these electrons screen from the nucleus. And so they're in between. Those 10 electrons are in between. So effectively, the outermost electrons, the valence electrons, the ones that you really care about that are on the outside, well, they're blocked a little bit by the interior electrons. And so that's why you end up with fluffy atoms. You know, as you go further and further down the periodic table, they get fluffier and fluffier because they can't see the nucleus as well as the inside ones. That's what it comes down to, okay? Let me make sure I hit everything here. Let me look through chapter 7 real quick and make sure I hit most everything. And we did some stuff. Make sure you go through and read that chapter, okay? There's some interesting stuff in there as far as the, you know, some little details and such. But, you know, as far as that goes, don't, you know, just go through it, okay? Now, that's it for me for chapter what do we got? 4, 6, and 7, right? Now look, as I said, I'm going to remind you at the very beginning, I said I cannot cover, nor do I intend to cover, every single minute detail of each chapter. Okay, well, this is an online class. You need to go through and make sure, you know, that you work as many of the red problems as you can. Good practice. But also keep in mind that if I didn't cover it, it's still important. It's just because I don't have the same time that I would have in a classroom, okay? So we've gotten a little bit further into the semester, but I just want to remind you that this is an online course. I shouldn't have to remind you that, but it is an online course, okay? But however, look, I've got my new WebEx address. Apparently it works because everybody's here, okay? By all means, hit me up on WebEx, email me. If you run into any problems, any questions, please let me know. Please let me know.